Welcome! In this presentation we will discuss how steep the road gradients typically are on real roads. We will also introduce one simplification of the gradient force expression and another simplification of the rolling resistance expression. This picture shows different gradients from -30 to +30% and the corresponding road inclination angle alpha in degrees. If we translate alpha into radians, we can see that the angle in radians is almost exactly the same as the gradient. This is a useful approximation and we will soon use it to simplify force calculations. Typical road gradients are within the range of roughly -10 to +10%. Even though it may not look like a steep gradient in the figure, already around 10% there are warning signs for longer gradients, since the driver may need to adapt the driving to the gradient. This is especially important for heavy vehicles like trucks. On normal road there exist gradients up to roughly 20%, but they are rare. There may be a few roads with gradients above 20%, but that can be seen as extreme cases which most drivers seldom will experience. Of course, different countries can have very different road gradients due to different topography. However, since heavy vehicles struggle both when driving uphill and when braking downhill, the roads cannot be very steep. In mountain regions, the roads are instead zigzagging to keep the gradient at a reasonable level. Next we will show a simplification of how the expression for gradient force vary with the road. We have already derived the gradient force as a function of inclination alpha, but since the steepness of a road most of the time is given as its gradient, we would like to use that value for our calculations. For small values of alpha, both sine alpha and tangent alpha equals alpha, if alpha is expressed in radians. Since gradient equals tangent alpha, and we now know that sine alpha equals alpha, and thereby also equals tangent alpha, we get that sine alpha approximately equals road gradient. This gives an approximate expression for gradient force, which is mass of the vehicle times g times road gradient. By plotting the approximation and the exact equation, we can see that they are almost exactly the same for low road gradients. Up to 20% gradient, the error is smaller than or equal to 2%, and even above 20%, the approximation is accurate enough for many purposes. If we use the approximation for the gradient force and compare it with the force required for acceleration, we see that they are very similar. From this we can notice that the gradient force has the same size as the force required for an acceleration if the acceleration a vehicle equals acceleration of gravity g times road gradient. This can be illustrated by an example. Assume a vehicle has exactly the right traction force to drive at a constant speed on a flat road. What would happen with the vehicle if it was driving with the same traction force in the same speed but on a gradient? On a -30% gradient, the gradient force will create a net force forward, which according to what we just derived will lead to an acceleration equal to the acceleration of gravity, 9.8 meters per second square, times the gradient, 30%, which is equal to approximately +3 meters per second square. Similarly, for -20% we get +2 meters per second square, and for -10 we get +1. And of course, the flat road is our reference case, leading to no acceleration. Uphill the acceleration becomes negative as the gradient force changes sign. +10% leads to -1 meter per second square, +20 leads to -2, and +30 leads to -3. This illustrates that the force from a -10% gradient is sufficient to accelerate the vehicle 1 meter per second square, or vice versa, a force which can accelerate the vehicle 1 meter per second square is sufficient to climb a 10% gradient at constant speed. We just introduced an approximation for the gradient force and will now introduce a similar approximation for rolling resistance. Rolling resistance is depending on the road gradient only because the normal force between the vehicle and the road is proportional to cosine alpha. However, for a small alpha value, cosine alpha is approximately 1. Therefore, for small alpha values, there is no significant dependence on alpha. The rolling resistance can be approximated as the rolling resistance coefficient times the mass of the vehicle times g. Thus, the approximate rolling resistance force is not a function of road gradient. The error of setting cosine alpha to 1 for different road gradients can be seen in this plot. It can be shown that the error is less than or equal to 2% for road gradients up to 20%. The simplified expression for rolling resistance also shows similarities with the simplified gradient force expression. This can be used to draw another parallel, which is useful when understanding what effect the rolling resistance has. It can be noticed that the rolling resistance force equals a gradient force if the gradient is equal to the rolling resistance coefficient. The exact rolling resistance coefficient of course varies for different vehicles, but on paved roads most vehicles have a rolling resistance in the order of 1%. Therefore, rolling resistance has a similar effect on the vehicle as driving up a constant 1% gradient. The effect of rolling resistance can be understood by a simple example. The rolling resistance is big enough to keep the vehicle stationary, but if the vehicle is on a 1% downhill gradient, that is just sufficient to make the gradient force equal to the rolling resistance force, and the vehicle will start to roll slowly. As you can see in the figure, 1% is a barely noticeable gradient. This example illustrates the fact that the rolling resistance is in fact a small force compared to gradient forces and acceleration forces. But as we will see later, the rolling resistance is still very important when analyzing the total energy consumption of the vehicle, since it is present all the time. Assume that a vehicle drives 100 km and it has to climb a 1% gradient all the time. That will lead to a total climb of 1% times 100 km, which equals 1,000 meters. So the rolling resistance caused the same energy loss over 100 km as the vehicle driving up a 1,000 meter high mountain. Summary. In this video you have learned that gradient force can be approximated as proportional to the road gradient. A -10% gradient leads to a force sufficient for +1 meter per second square acceleration. Rolling resistance is approximately independent of the road gradient, and rolling resistance force has a similar effect on the vehicle as a constant 1% uphill. Road gradient typically stay within ±10% on most roads, but steep road gradients up to 20% occur. More than 20% can occur, but is considered to be extreme. Thank you for watching.